Nice meeting everyone from Access so far. One day, staring at this lovely figure while sitting in my not-so-lovely basement office, something dawned on me. The EPA, or the Environmental Protection Agency's PM 2.5 air pollution sensor network, is really unequally distributed. We have way more sensors in the eastern half of the United States than in the west. There's a prioritization of urban areas over that of rural ones, and there's a higher density along the coasts rather than more inland. The reason for why this is stems from the history of air quality policy and regulations in America, but there's a problem. But before I get to that problem, let me provide a little bit more background. So many of us are familiar with PM 2.5 or particulate matter aerosols that are less than 2.5 microns in diameter across. They're very well known for their adverse effects on human health and their forcing terms on climate. However, what really interests me about PM 2.5 is its unique multi-scale behavior. Multi-scale in that it varies quite a bit in both space and time. In terms of space, PM 2.5 can come from a variety of different sources, from natural sources such as dust in the desert southwest, to human or anthropogenic sources such as factories or on-road transportation and diesel trucking. PM 2.5 is also very sensitive to meteorological conditions. Depending on the weather, PM 2.5 can be immediately washed out from a convective thunderstorm, or smoke from a wildfire can travel slowly across the country if there's a favorable breeze. If we look at PM 2.5 trends in time, we see that on the right, over the last 20 years or so in the United States, the average PM 2.5 concentrations have been getting cleaner, have been getting lower. This is because we're putting scrubbers in power plants and catalytic converters in cars, and through air quality regulations, we're actually cleaning up air pollution in the United States. So if we revisit the figure from before, we can understand that this configuration of the EPA sensor network was really optimized for 1980s and 1990s air pollution in mind, when there were three dominant drivers, one being cities, urban areas produced the most pollution. Two, from on-road vehicles and transportation, freeways, diesel trucking. This was a large source in the US. And three, from power plants. That's why we see so many of these sensor locations found in the Midwest. But as we know from decades of successful air pollution regulations, this has really improved these sectors in the United States in terms of air pollution. However, a lot of this will be undone with the recent growing source of wildfires, largely stemming from the western United States. And so there's this idea that perhaps this EPA sensor network is not correctly optimized to capture this new growing source. This new idea that the rise of low-cost sensors and citizen science and volunteer monitoring networks might be able to fill in the gaps left by the EPA. So the EPA network is very expensive to set up and deploy. Each of those dots on that map costs $250,000, and that's not even considering the upkeep afterwards. However, low-cost sensors, here showing Purple Air being the largest company that deploys these sensors. Anyone can buy a sensor from Purple Air, put it on the outside of their home, and connect it to the internet to upload concentrations of PM 2.5 in real time. And it's been really championed as this democratizing tool for air quality data. However, this really great paper by Priyanka D'Souza, she finds that these Purple Air sensors are deployed in significantly wider and higher income census tracts relative to the national average. So there's this built-in racial and income bias to these sensor deployments. And two, that these Purple Air sensors are deployed in locations that actually have lower annual average PM 2.5 concentrations than those with an EPA monitor. So they're also deployed in cleaner areas, which suggests that we have to design these sensor networks intentionally rather than leave it up to volunteers or up to chance. And that left me with two questions that I wanted to answer. One, can we design a new optimal data-driven sensor network for the United States? Optimal meaning that we capture the largest pollution drivers of today. Data-driven meaning that we use air pollution information rather than one based on intuition. And two, are there gaps in the coverage for the current EPA network? That the EPA, it's a very finely tuned network, and it actually might be doing pretty well. And so in order to design a nice data-driven sensor network, I need pretty good underlying data. And luckily, this dataset came out from the Harvard Public Health School just when I was starting this project. I have 17 years worth of daily data at 1 kilometer resolution of PM 2.5 in this nice gridded high resolution format. How the dataset is made is basically combining sparse measurements from surface networks and satellite observations of AOD and combining it in an ensembled machine learning fashion with land use, weather variables, model outputs, and it creates this nice gridded data product. And you can kind of see the dynamics of PM 2.5 that I described earlier, where you can have an influx of pollution, whether that's from a wildfire or an industrial point source, and that pollution plume can either be rained out immediately or travel across the entire United States if there's a favorable breeze. I really did not want to design a PM 2.5 sensor network based on average or mean PM 2.5 concentrations, which would involve placing a sensor where the spatial gradients in the mean surface would fall off. I really wanted to capture the extreme pollution episodes found in the data that may otherwise be averaged out, such as a wildfire or a short-term temperature inversion. And so in order to capture these extreme events, we use something called dynamic mode decomposition, which can better uncover a lot of spatial and temporal structure in the data. How it works is step one is I collect my 17 years worth of data at daily resolution. Each snapshot is the contiguous United States. Step two is organize them into a matrix X, where one axis is space, so latitude and longitude squished into one dimension, and the other axis is time. Then I have that same matrix X that's time shifted one time step into the future, X prime. And what DMD here, dynamic mode decomposition, attempts to do is create this best fit linear approximation A that approximates the evolution of PM 2.5, both in space and time. And what that gives us is some kind of average background variability of PM 2.5 and can separate that from high pollution, shorter term episodes. And here I'm showing you a kind of complicated looking figure, but I'll walk you through it. The idea is that any kind of mathematical operation we do, if we do it on a really long-term data set, it's inevitable that shorter-term pollution episodes, such as a wildfire, will get averaged out. And so in order to incorporate a greater amount of transient information into our kind of library of information that we want to build, we adopt a multi-resolution framework. That's what MR in front of DMD in this title shows. And that sounds kind of fancy and jargony, but basically it just means we do this DMD operation on different time chunks of our data. So how it works is I have some kind of long-term time series in which I do DMD on that. I then save that spatial and temporal information from that long-term time series, save that, and then take my time series, cut it into half. Now I have two chunks. On those two chunks, I perform DMD on those two separate chunks, save that spatial temporal information into some library catalog, and then cut those two chunks in half. And we do that until our shortest frequency cut is 1 day. So now I have this huge library of spatial and temporal information, and what we do is apply a simple filtering or a simple threshold function that says if you are within 10% of the signal or 10% of the variability of this really long-term time series spatial temporal information, then you're just noise on top of that background. However, if you exceed this threshold, you are considered a significant polluting event, and you're cataloged as a sort of colored square in this calendar figure. And how to read this is that on the x-axis we have time, and on the y-axis is we have those different time chunks. And so I have to note here that the x-axis here is only for 11 years. This is because halving of that data, going from 1, 2, 4, 8 days, etc., we get to around 11 years before running out of data. So here I show the first 11 years of this data set to kind of illustrate this idea. And we see that for the long-term spatial temporal mode, we call it, that generally variability of pollution is higher in the east than in the west, except for parts of California. But generally, we see that most pollution episodes occur between 1 week and 1 month. And this is actually pretty good to know because PM 2.5 has an atmospheric lifetime of around a week in the atmosphere. So it makes some kind of physical, intuitive sense. And so what I wanted to do is, because there's so much information in this figure alone, I wanted to see which polluting episodes, what do each of these polluting episodes mean? So here I select one that lasted for almost 9 months between 2007 and 2008, with the hotspot signal coming from the Central Valley in California. I go and look in the San Joaquin Air Pollution Valley Control District and find that this was actually an anomalously bad time for PM 2.5 pollution in the valley. There was a prolonged winter temperature inversion that capped pollution there. And this is a pretty well-known area that exceeds EPA sort of air quality criteria guidelines. So let's look at another pollution episode. This happened in the summer of 2007, and the hotspot that we find is in Idaho in northern Utah. A quick Wikipedia search shows that this corresponded exactly with the Murphy Complex fire, that this was a significant pollution episode above background PM 2.5 variability. And so what's really cool about this idea is that because our underlying data set contains real-world measurements from satellites and surface observations, that we can actually pick out specific high pollution episodes and incorporate them into this library of information that we're constructing. And so we can use that information from that library that I just showed you of the most extreme PM 2.5 polluting episodes and place sensors that can capture the most information from those events. And the result I show is here, where on the top I have the EPA sensor network of PM 2.5 that we make comparisons to, and those on the bottom for this DMD data-driven sensor network. And so if we look through the different regions, we see that in the northeastern Atlantic seaboard that we match the EPA sensor network pretty well, just with a reduced density. If we look in the Great Lakes, there's a large EPA presence there due to the very turbulent meteorological conditions from the Great Lakes, and the DMD also says that there should be sensors there. And that generally we track the EPA network in the east just with a fewer number of sensors. However, the story really changes in the western US, where only a third of the total number of sensors of the EPA are placed in the west, whereas over half of those from the DMD are there. And although both actually have around 700 total sensors, that the distribution is actually quite different. We see that the DMD data-driven sensor network suggests that the EPA monitoring network is under-monitored in Northern California and in the Central and San Joaquin Valley. For example, the EPA has 15 sensors in the San Joaquin Valley, and DMD says that there should be 5 times as many. This is a very polluted area of the country. It's basically where America's fruits and vegetables are grown, and it regularly is out of attainment for PM 2.5 standards. In Northern California, this is basically wildfire country, and there's an under-monitored presence there as well. To conclude, this is one of the first kinds of studies to design a sensor network based on the extremes of air pollution. And I leave here some future extensions, and thank you so much for your attention.